Good morning. Welcome back. So, friends, in the last video lecture, we have seen what is the need for programming and how programming languages evolved, how programming languages came into existence. Along with that, we have also seen the programming paradigms, uh, which includes procedural programming, structured programming, and object oriented programming. There are so many other programming paradigms, but we have only discussed three fundamental programming paradigms. And C programming language will come under structured programming language. And to certain extent, we can even say it is also procedural programming language because it is code centric. So in continuation to our previous video, where we discussed all these things, need for programming and evolution of programming languages. Today, as part of continuation, we will discuss memory addressing concept, right? So the concept is memory addressing, which is very, very important. Without understanding memory addressing, nobody can become a good programmer. That is the reason memory addressing is a very, very important concept. And in order to understand memory addressing, first we should have a look at block diagram of a computer. This is very, very important. So please observe here. You can see a block diagram of a digital computer. The two most important components of the digital computer are CPU processor, you are aware of it, I hope, and main memory, which is also called as the RAM. Right. Apart from that, you have various I/O devices, input output devices. But the most important point to be observed in this diagram is CPU is directly connected to main memory. That is, CPU is directly interacting with main memory. CPU never interacts with any other memory device or any other IO device directly. So that is the important point to be observed in this diagram. Right. There are several reasons like why CPU does not interact with other devices. One common reason is CPU is a high speed device, very, very fast device, and generally the IO devices are very, very slow. Right, that's the reason CPU will never interact with these devices directly, and comparatively main memory is a very fast device when compared to other IO devices. So CPU directly interacts with main memory. So whatever data or program which has to be processed by CPU should be loaded into main memory, right? So there is a concept called as a stored program concept, based on which the first electronic computer was developed by Mr. John von Neumann. So as per John von Neumann, right, any program or file which has to be processed must be stored in a place or must be made available to CPU. So that place is nothing but main memory. So CPU directly interacts with main memory. So why are we talking about block diagram of computer here? The reason is because we are going to write programs, right? And in program, the two basic elements of any program, right? Two basic elements we have discussed in our previous lectures also. Two basic elements, two basic elements of any program are, what are the two basic elements? Code and data. So friends, here the point is two basic elements are code and data. Now where the data gets created? We have a hard disk in our computer, we have main memory in our computer, we have other external removable storage devices like CD drive, DVD drive, or a pen drive, USB drive, etc. So where my data gets created, if I write a program, right? Program involves code and data. If I write a program where the data gets created, that I should know very clearly, right? So data gets created inside main memory, right? Now the point is very clear. Why data gets created inside main memory means you can look at the block diagram. Main memory is directly accessible by CPU, so the data must be created inside main memory, right? So this is what is the reason, like why data gets created in main memory, because CPU directly can access main memory. Now the point is, okay, now CPU interacts with main memory and my data gets created there. Now how this main memory is organized, right? Generally, what is the size of the RAM? Generally, what is the size of the RAM? Main memory is nothing but your RAM, right? So if you buy a computer, generally what is the size of the RAM, right? Maybe 8 GB, something like this, right? 16 GB, right? So how this 8 GB, 16 GB, 4 GB, how this entire main memory is organized, that is very, very important, right? That we are going to understand now as part of a concept called as memory addressing, right? Because generally when we create data in our program, we create data like maybe a 1 byte, 2 bytes or 4 bytes kind of data which we need generally. For example, in my program, if I want to add two numbers, so first of all, I need to store those numbers, and to store an integer in C programming, hardly I need 2 bytes. Hardly I need 2 bytes. And to store two numbers, I just need 4 bytes. Now, out of 8 GB RAM, suppose I have 8 GB RAM, right? 8 GB is a huge amount of space. And in that, if I am asking just 2 bytes of memory, where I will get those 2 bytes of memory? In which part of main memory the 2 bytes will be allotted? I should know the address of that 2 bytes, then only I can access that 2 bytes of memory, because 8 GB means too much. 8 GB is a huge amount of memory. So let us understand how this 8 GB, 16 GB, whatever may be the size of the RAM, how this main memory is organized and how main memory addresses are created, right? So this is what is the concept of memory addressing, and we are trying to understand that clearly, right? So the concept is memory addressing, right? Concept is memory addressing. I'm sorry. Yeah, memory addressing. So much before that, one should understand the terms of bits and byte. So if you are aware of it, well and good. If you are not aware of it, let me tell you. So what is one bit? One bit. Friends, bit stands for binary digit. So what is a bit? Bit means binary digit. Binary digit means what? Either, what is a binary digit? Either 0 or 1. So one bit is nothing but either a 0 or 1. One bit. Bit stands for binary digit. So friends, here let us understand the terminology. 8 bits is equal to 1 byte. So friends, 8 bits is equal to 1 byte. So please try to understand the terminology used here. Please try to understand 8b, small b always represents bits. So 8b is equal to 1 byte. Capital B always represents a byte. So this is the relationship. So one bit means how many, 1 byte means how many bits? 8 bits. So I can also say 1 byte is nothing but 8 is written as 2 power 3, right? So I can write like this. 1 byte is 2 power 3 bits. So 1 byte is 2 power 3 bits. Nothing but 8 bits. Fine. So I hope till this point it is clear the relationship between a bit and byte. One byte is 8 bits. One byte is 8 bits. 8 bits is also called as 2 power 3. 2 power 3 bits, right? I hope till this point it's clear. Right now, now see here. One second. So 8 bits is equal to 1 byte. Now 1k, sir, 1 kilobyte. So 1k. See here, I am not writing bit or byte. I am just saying how much is 1 kilo. 1 kilo is 2 power 10. 1 kilo is 2 power 10. 1 mega is 2 power 1 mega is 2 power 20. Similarly, 1 giga is equal to 2 power 30. So I'm talking about only what do you mean by a kilo, mega, giga. So it can be bit or byte. If I put a small b, it becomes bit. If I write a capital B, it becomes byte. So if I say 1 kb, if that b is small b, I say it is 1 kilobit. If that b is capital B, I should read it as 1 kilobyte. So that is how it is represented. So what is 1k 2 power 10? Means 1024. What is 1 mega 2 power 20? 1 giga is 2 power 30 and 1 terabyte is 2 power 40. So you call it as byte or bit, it is depends on whatever you write there, but 1 tera is 2 power 40. 1 peta is 2 power 50 and 1 hexa is equal to 2 power 60. Similarly, 1 iota is called as is equal to 2 power 70 and 1 zeta is 2 power 80, right? So this is the relationship or this is the meaning of 1k, 1m, 1g, 1t. So 1 kilo is 2 power 10, 1 mega is 2 power 20, 1 giga is 2 power 30, 1 tera is 2 power 40, 1 peta is 2 power 50, 1 hexa is 2 power 60, 1 iota is 2 power 70 and 1 zeta is 2 power 80. Right friends, so I hope till this point it is clear. So let us move on. So let me clear this if possible. Yeah. Right. So now suppose I have a main memory of size 8 GB. Suppose I have a main memory of size, one second, the pen is not selected. One second. Sorry for the disturbance. Yeah. So yeah, so we have seen what is the relationship. We have seen the relationship like what is 1K, what is 1M, what is 1G. So now if I say I have a main memory, suppose if I say I have a RAM of size 8 GB. So what do you mean by this? If I have a RAM of size 8 GB, so how many bits it is or how many bytes it is? So 8 is nothing but 2 power 3. Giga is nothing but 2 power 30, right? So I call it as bytes. So total how much it is? It is 2 power 33 bytes. I can also write it like this. 2 power 33, right? I can also write it like this. 2 power 3 is 8. 2 power 30 can also be written as 2 power 10 into 2 power 10 into 2 power 10. Right? Can I write like this? 2 power 30 is can also be written as 2 power 8, 10 into 2 power 10 into 2 power 10, right? Bytes. So to make our calculation easy, I can say 8 into, now what is 2 power 10? It is 1024 into 1024 into 1024 bytes. So friends, how much is 8 GB? How much is 8 GB? 8 GB is equal to these many bytes. 8 into 1024 into 1024 into 1024 bytes. So I hope now you understood how much is 8 GB. And generally, the job of memory management is done by operating system. So memory management is the job of operating system. So when I run a program, in that program, if I need some data to be created, operating system allots me the memory from main memory or RAM. So how much memory generally we ask very small amount of memory. So suppose I want to store one integer, I just need 2 bytes. But how much memory I have? I have a very big memory of 8 into 1024 into 1024 into 1024 bytes, or simply you can say 2 power 33 bytes of memory I have. And in that, if I just need 2 bytes, so how do I access 2 bytes from such a big 8 GB RAM? So operating system has to return me the address. Operating system has to return me the address of the 2 bytes so that I can access it. So that's the reason one should understand how addressing is done. How addressing is done. So let us try to understand addressing using this simple example of 8 GB RAM. So imagine I have a RAM of size 8 GB. So friends, whenever you want to do memory addressing is done based on the size of your processor. So what do you mean by this? What do you mean by this? Size of the processor means size of the processor. So what do you mean by size of the processor? Size of the processor means how many bits your processor can process at a time. You might have heard like 32-bit CPU, 64-bit CPU. I hope you know this, right? So 32-bit CPU, 64-bit CPU, what do you mean by this? 32-bit CPU means your CPU can process 32 bits at a time, right? So suppose if I say 32-bit, this is called as size of the processor. So 32-bit processor means it can process 32 bits at a time. 64-bit processor means it can process 64 bits at a time. So that is the meaning. Now, whenever we divide our main memory, now this 8 GB RAM has to divide it into pieces, right? So that I can access a particular byte. So main memory will be logically divided into pieces, and size of each piece will be equal to 32 bit if the processor is a 32-bit processor. If the same 8 GB RAM is kept inside a 64-bit computer, then the main memory will be divided logically into pieces such that size of each piece is equal to 64-bit. So 8 GB RAM, if it is kept in 32-bit machine, then it will be divided into pieces. And how many pieces I'll get? 8 GB divided by 32-bit. That will give me the number of pieces because 8 GB is my total RAM. Size of each piece is 32-bit. So let us do that simple math to understand how the main memory is logically divided into pieces, right? We'll take a new slide. Right. So where we are. So what is the size of my RAM? My RAM size is 8 GB, right? One sec. Yeah. So my RAM size is 8 GB. And what is the processor? My processor is a 32-bit processor. So the RAM will be divided into should be divided into pieces such that size of each piece will be 32-bit. So now the question is how many pieces I'll get. So I need to do a simple division, right? I need to do a simple division. 8 GB divided by 32-bit. 8 GB is the total RAM size and size of each piece is 32-bit. So I have to do this simple division so that I'll get the number of pieces, right? So how you understood this division why I'm doing? Suppose I have 1 kg cake. I have 1 kg of cake and I want to give it to 4 students and each student should get equal piece. So 250 grams it will be divided, right? 250 grams into 4 pieces. It will be 1 kg. So if I want to give 250 grams to every student, I'll get 4 pieces. Similarly, I have 8 GB RAM. I want to divide it into pieces. Size of each piece is 32-bit. So what I want to calculate now, if I divide my 8 GB RAM into 32-bit pieces, how many pieces I'll get? So this division will tell me how many pieces I will get. So please observe here. So what is 8? 8 is nothing but, okay, let me write it. 8 is 2 power 3. Giga means 2 power 30. B as it is. And here 32-bit means how many bytes, sir? 32-bit is 4 byte because we know the relationship between bit and byte. 1 byte is 8 bits. 32 bits means divide by 8 you will get 4 bytes. Now this B and B got cancelled. Now this is 2 power 33 because bases are equal, power should be added, and this 4 can be written as 2 power 2, and this 2 power 33 minus 2 you will get 2 power 31. So what is this 2 power 31? 2 power 31 pieces you will get when this 8 GB RAM is divided into pieces such that each piece is 32 bit. You will get 2 power 31 pieces. So friends, please observe this carefully. Your main memory or RAM will look like this. Your main memory or RAM will look like this. So it will be divided into pieces, right? Each piece is 32-bit, my dear friends. Each piece. So like this, how many pieces I am getting? I am getting 2 power 31 pieces. It's a very big number, right? And in each row, what is the size of each piece? 32-bit. 32-bit means how many bytes? 4 bytes. Means in each row I'll get 4 bytes. So I can draw a line like this. right? So in each row, this is one byte, second byte, third byte, fourth byte, 32 bit. It is 32 bit, right? Row 1 is 32 bit, row 2 is 32 bit, like that. Each row is 32 bit. 32 bit means 4 bytes. So each cell is 1 byte. Now for every byte you have to give a unique address. That is what is memory addressing. Now the point is, since computer understands only the language of ones and zeros, I should give addressing, I should give address to every memory location using binary number system only. So each row is one memory location now. So what is each row? Each row is one memory location. So each row is one memory location. One memory location. In each location, how many bytes we have? In each location, we have 4 bytes. How many locations we have? We have done the math just now. We have 2 power 31 locations. Now the point is, if I give binary address, then how many bits I need to generate a binary address? So friends, simple logic, please try to understand. Observe here. Suppose I have only 2 bits. Suppose I have 2 bits. With 2 bits, how many combinations, how many different binary combinations I'll get? With 2 bits, I'll get 4 different binary combinations: 0, 0, 0, 1, 1, 0, 1, 1. So with 2 bits, I'll get 4 different binary combinations. Means each binary combination can be used to can be used as one memory address. But with 2 bits, how many how many memory locations can be addressed? Only 4. Means with 2 bits, how many combinations I'll get? I'll get 2 power 2 different binary codes. Each binary code can be used as one memory address. Means with 2 bits, I'll get 2 power 2 combinations. With 3 bits, how many combinations I'll get? I'll get 2 power 3 combinations. With 4 bits, how many combinations I'll get? I'll get 2 power 4 combinations. With 30 bits, how many combinations I'll get? 2 power 30 combinations. With 31 bits, how many combinations I'll get? 2 power 31. Yes or no? Now here, how many different memory locations we have? We have divided our 8 GB RAM by 32 bit. So how many pieces we got? We have done the math, right? We got 2 power 31 pieces. So if I use a 31 bit binary code, how many different binary codes I'll get? 2 power 31 combinations. 2 power 31 combinations. So 31 means I need a 31 bit binary address now. Yes or no? Because that 2 power 31 with 31 bits, you will get 2 power 31 different binary combinations. So how many memory locations I have? 2 power 31. So I should use a 31 bit binary code, something like this: 0, 0, 0, 0, 0, 31 zeros, and last location is 31 ones. So like that, with a 31 bit binary code, with a 31 bit binary code, we will get 2 power 31 different combinations, and we have 2 power 31 different locations in our memory. So 31 bit binary code will be sufficient. Now the point is, if I use 31 zeros, right? If I say the address is 31 zeros, I am representing which memory location? I am representing which memory location? I am representing the first memory location. If I say 31 ones, I am representing which memory location? The last memory location. But if I say 31 zeros, I represent first memory location. But in each memory location, again, there are 4 bytes. So with 31 zeros, at the max, I can reach to the first memory location. Yes or no? At the max, I can reach to first memory location. But in that first memory location, which byte I want? Either first byte or second byte or third byte or fourth byte. Means for every byte, again, there should be a unique address. Yes or no? Again, I need a separate address for every byte because 31 zeros, it is incomplete now. Because suppose if you have ordered something in Zomato, right? You ordered some food in Zomato, and imagine the delivery boy came to your street and he called you saying that, sir, I reached your street, road number 2, I have reached. But in this road number 2, there are four houses. Which one is your house? Then you will help him, right? You will say like, the third house is mine, the fourth house is mine, something like that. You have to guide, otherwise he will come to your road number 2 or street number 2, but exactly he can't identify which is your house. Similarly, with the 31 bits I can reach to a particular memory location, but in that which byte you want. So for that, again I need two more bit address, because in each row how many cells we have? Four, right? So first byte, second byte, third byte, fourth byte. So for these bytes also I should give a unique address. So again, for four, 2 bits are enough. We have done the calculation in the very beginning, like with 2 bits how many combinations I'll get? Four combinations: 00, 01, 10, 11. So see here, so I can call this one as 00, and I can call this one as 01. I can call this one as 10, and this one becomes 11. So 31 plus two more bits I need, a total of 33 bit. A total of 33 bit address is required. Yes or no? 31 plus 2, a total of 33 bit binary address is required to access a particular memory location. So friends, why are we talking about memory addressing? Why memory addressing is very important? The reason is very simple. Whenever we write programs, we create data. Suppose I want to create an integer. Integer needs 2 bytes. Now how much memory I have? I have 8 GB, such a big amount of memory. In that, which 2 bytes I'll get? I don't know. Operating system will allot, will do the memory management. So who allots the memory? Who allots the memory for you? Operating system. So operating system will allot 2 bytes. Imagine, just imagine, if there is a conversation between operating system and compiler. What is compiler? Compiler is a software which converts your program into machine code, right? So on behalf of you, on behalf of the programmer, compiler will ask, like, I need 2 bytes of memory. So it's like an interaction between compiler and OS. Imagine if compiler is asking, OS, please give me 2 bytes to store one integer. And if OS says, yes, I have given. If the response of OS is, yes, I have given. Do you think it is sufficient? No, it is not sufficient. OS has to tell which 2 bytes it has given. Means it should return the address. And you have seen address. What is the address? For 8 GB RAM, you are getting a 33-bit big binary address. So OS generally returns the memory address when it allots the memory. So when compiler asks, no, OS, please give me 2 bytes to store an integer, then what OS does? Somewhere in the main memory, as per its convenience, OS will allot the memory, and it will return the starting address of the first byte. Suppose 2 bytes are required for integer. In that, it will return you the address of that first byte, which is a 33-bit binary code, right? Since I cannot remember such a big address, 33-bit binary address, what we will do? We will try to use a concept called as variable. Variable is nothing but it's a name given to a memory location. Since I can't remember 33-bit, 31-bit, or 34-bit, or 35-bit binary address, I'll try to store that in a variable. So variable is simple. It's a name given to memory location. So we'll try to give name to a memory location. So giving name to memory location is called as variable. So why are we giving name to memory location? Means this is the reason behind it. Memory locations will have memory address. Memory address is very, very big, and I can't remember such a big lengthy memory addresses. So we try to give name to that memory address. So friends, this is how your main memory will look like. And whenever you create data in your program, data gets created inside main memory. Since main memory is well organized, it is properly divided into rows and columns, and every column, every byte is uniquely addressed. It is very easy for us to access main memory because of this memory addresses. But memory addresses are very lengthy. I can't remember them. 33-bit binary code, I can't remember. Suppose I want to create three integers in my program. So three different uh, three times memory allocation has to be done, 2 bytes each for every number. Now three different memory addresses will be returned, means three 33-bit binary codes. Can I remember three 33-bit binary codes? No. That's the reason we try to give name to that memory location, like a comma b comma c, so that it becomes easy for me. So I hope, friends, the concept of memory addressing is clear, and why we are giving name to memory locations. The reason is very simple. I can't remember such a big memory location, address of such a big my binary address I can't remember. So I'm giving name to that memory location, which is called as variable. So this is how the main memory is divided logically into pieces, and this concept is called as memory addressing. And whenever we create data in our program, data gets created inside main memory. And if you know how main memory is organized, right, it will be easy for you to understand uh, how your data gets created, where your data gets created, right? What do you mean by a memory address? When you know all these basics, when you know how, when you can imagine how data gets created and stored inside your computer, then only you can process the data easily. At the end of the day, programming is nothing but doing some processing on the data. And if you don't know how exactly the data gets created, where exactly the data is stored, what do you mean by an address, how addresses are assigned, so without having this kind of fundamental knowledge of memory addressing, obviously you can't write a better program. So that's the reason memory addressing becomes a very important concept for any programmer to become a good programmer or to write better programs. So finally, what is a variable? Variable is a name given to a memory location. Why are we giving name to memory location? This is the reason, right? I hope you understood the concept of memory addressing and importance of memory addressing, right? So in the next video lecture, I'll come up with other basic fundamental concepts of C programming. We will see structure of a C program, then followed by data types, operators, operator precedence. So in a systematic manner, we will move and we will give complete knowledge of C programming, so that you can do lot of C programming, hands-on experience you will get. You can do lot of programs on your own. We will also tell you what kind of programs can be done for practice. We'll give you lot of questions, right? We'll share that also. So as of now, as part of prerequisites, we have seen two important video lectures. One is need for programming, another one is memory addressing. So thank you. We will meet in the next video lecture.